Hey everyone, welcome back. In this last video of our lecture 4 of the semester, I'd like to just compute a couple of examples. We spent this lecture deriving the dot product and then using the dot product to write down formulas for different kinds of projections. So in the first example, I'd just like to compute some projections with actual numbers. So let's remember, I'm going to write down formula for the projection of u onto v. This one, in terms of computing, we did the whole geometric setup. Now that we know what it means, we just have to remember how to compute it. It's u dot v over, I'm going to do the length of v squared times v. This is also v dot v, right? Similarly, we have our component projection. And this one is given by u dot v over just simply the length of v, and that's kind of why I wanted to write it that way. And then finally, our orthogonal projection. This one's always going to be u minus the actual projection. So let's compute these, and then we'll change the roles of u and v as well. But let's compute these ones first. All right, so first of all, I think we should just, for this one, start by computing the different pieces that we need. We are going to need u dot v. We are going to need length of v, right? And let's just start with length of v squared because we know how to compute that pretty easily, v dot v. So let's start with u dot v then. U dot v is -4, 1, 2, dotted with 1, -2, 2. And of course, the dot product just goes component by component, add them up, right? So this is -4 minus 2 plus 4. So this one is just what? -2, right? As I make a typo, is -2. So there's our dot product. We need to also compute v dot v. So this is just the sum of the entries squared and then not square rooted, right? But that's the length squared, remember. So this is 1 squared plus -2 squared plus 2 squared. This is 1 plus 4 plus 4, so this is 9. And then of course, if that's 9, the length of v is the square root of 9, which is 3. All right, so this information can be used to build the first two of these, and then we just have to do a little subtraction to get the rest of it. So let's start with our proj then. Projection onto v of the vector u. This is going to be, I'm not going to rewrite the formula, just plug the pieces in, right? So it's -2 divided by 9 times the vector v. So 1, -2, 2, and I'm going to distribute this out. So this is -2 ninths, +4 ninths, and then -4 ninths. Okay, so there's our projection of u onto v. The component projection is just a number, right? So the comp here onto v of u. This is dot product, -2, divided by length of v, but not the length of v squared, just the length of v. So 2 -2/3. That's it, that's the answer, right? And so then for our orthogonal projection, for this one, we're going to have to use the vector u itself. So the vector u is -4, 1, 2, minus the projection that we just computed. So we don't have to recompute it. We've already got it. And we can just now very carefully perform these operations, right? So this is -4 plus 2 ninths. So 4 ninths is 36 plus, it's -4, so that's going to end up being -34 ninths. 1 minus 4 ninths, so that's going to be 5 ninths. And then 2 minus a negative, so 2 plus 4 ninths, that's 18 plus 4 is 22. So there's the orthogonal projection. All right, let's now repeat all this. So these are some of our answers. Let's repeat all of this by just switching the roles of u and v. And before we do that, just think about, do you think that the answers are going to be the same or not? So let's say u looks something like this, and v looks something like this. So I think I'm switching the colors from the last video, but that's okay. Then the projections that we just computed are u onto v. So what we just computed, right, is this vector in this direction. But if you look at the other one, the projection of v onto u, this is what we're going to do now, that's going to be very different, right? They're not going to be the same. The magenta and the light blue are not the same vector there. But for us, one of the things here is not going to change. So this dot product, we don't have to recompute. We know that that's -2, right? What we need instead is we need the length of u and the length of u squared. So I'm not even going to rewrite these formulas. I'm just going to go by, in my mind, switching the u's and the v's. So if that's dangerous for you, pause the video, write down the formulas, okay? So the projection, the first thing we need is u dotted with u. Remember, this is the length of u squared. Go back up to u. U is -4, 1, 2. So this one length squared is -4 squared plus 1 squared plus 2 squared, 16, 17, 21. All right, and this means that the length of u is the square root of 21. And 21 has no perfect square factors. It's 7 times 3. They're both prime. We leave it. Square root of 21 is a perfectly good number. Okay? All right. So the projection then onto u of v this time, this is going to be equal to, I guess I will write the formula. It's u dotted with v over the length of u squared times the vector u. So remember, this is -2 over root 21 times the vector u. That's -4, 1, 2. And then again, we can distribute. So this becomes +8 over root 21, -2 over root 21, and then -4 over root 21. So there's our projection of v onto u. The component projection is very easy to do once you've done all this work. You've already done all the work, right? So it's v onto u. This is the dot product, so -2 divided by, oh boy, I messed up, didn't I? I'm sure you guys are yelling at me. So I used the length of u here. I should have used the length of u squared, right? It should be 21, regular 21. So this part is actually 21. And down here, this is the root 21, right? That's square root 21. Okay, now can we reduce any of this? No, 7 and 3. Nope. Okay, so I messed it up, but we fixed it. So whenever you make a mistake, as long as you catch it before you have to submit it and get graded on it, you're good to go, right? And so the last thing we have to do then is compute our orthogonal projection. And this is now going to be v minus the projection onto u of v. All right. So remember our vector v, scroll up if we forget, is 1, -2, 2. 1, -2, 2. And we need to subtract this projection vector. So that's 8, 21, -2 over 21, -4 over 21. And then we just combine these like terms. So 21 minus 8 is 13. This is -2, so -42 plus 2. So that's -40 over 21. And then 42 plus 4, +42 plus 4, that's going to be 46, 21. And so there's our orthogonal projection. Okay, I've got one more example for us here. These are the answers, though, to the second part of that. That's all the projections you could possibly want. This one says, use a scalar projection to show that the distance from a point P, x1, y1 to a line, ax plus by plus c equals 0 is given by this formula here, and then use it to compute something. So this is an example that is close to my heart. It's geometry. I love this stuff. So let's sketch a picture and then try to see how the scalar projection is even going to help us. All right, so here's our, let's say, this is our x and our y axes. Let's say the line does something like this. So this is our line L. It's given by ax plus by plus c equals 0. And let's say the point is maybe up here, x1, y1. All right, and then let's do a couple of things here. We need to figure out how we're going to measure the distance here by a projection. So the first thing we need to know is what's the distance, right? So the distance always means the shortest distance, the orthogonal distance. This distance d right here, that's supposed to be orthogonal symbol or perpendicular symbol. That's exactly what we want, right? So what we have to do then is make a couple vectors and then try to do a projection, because that's what it tells us to do, right? So one of the vectors that we can choose, we need a point on the line, any point on the line. So I'm going to say we can probably find that point, the point where x is equal to 0. And then we can use this point to make one vector. All right, there's a vector. that connects the point on the line, which I'm going to choose the one where x is equal to 0, to the point P. So we'll know exactly how to write that one down. And then we need to project it onto something. But what are we going to project it onto that's going to give us this distance? Well, we need to project it onto a vector that is orthogonal, perpendicular to the line, right? So this will be our vector v perpendicular to the line. Now, by the way, the projection now is going to be, it's going to be this one, right? It's going to actually give us this. But the length of this and the length that we're looking for are the same. So that's the goal. Now, the slope of the line we can compute, right? And then we can use the slope of the line and the fact that the slope of a perpendicular line is a negative reciprocal, opposite reciprocal sometimes, to write down a vector that, you know, for v here, a vector that represents this v. So let's solve this thing for y. So if you're going to solve this for y, this would say that y is equal to what? Negative a over b x minus minus c over b. Okay, so this tells us two things. It tells us that the height at this point is negative c over b. So that's going to help us build this vector, right? The minus c over b, because that point then has coordinates 0, minus c over b. So that's good. And then the second thing that it tells us is that the slope of the line is negative a over b. So the direction vector of the line, so VL, the direction vector of the line, this is rise over run, right? So the direction vector of the line is b minus a, or minus ba, it doesn't matter. All right. The negative reciprocal of this is, of course, positive b over a. So the perpendicular slope, right? The perpendicular slope, m, perp, is going to be b over a. And then, again, it's rise over run. In our vector, it's got to be run and then rise, right? Rise over run, run and then rise. A comma b, b over a. So this right here is the vector that we want. That's it. That's the one right there. We're going to project onto this vector. But we really only need to do a component projection, right? So the other thing we need to know is this u, this magenta vector here. We need to build this. So let's call our vector u. The vector, we'll call this maybe AP, because it's not the origin, right? That's point A. AP. But it's always terminal minus initial components, right? So the way I've set this up is it's going to be x1 minus 0. So just x1. And then it's going to be negative y1 minus, so y1 plus, right? y1 minus a negative c over b. Okay? And so we can rewrite this then as x1 comma y1 plus c over b. And remember, our v is going to be this right here, ab. And now we just need to use the formula for the scalar projection, because the scalar projection is going to give us exactly the number that we want. It could technically be negative, right? So we're going to take the absolute value of it as well. So this is what we want. Our distance is equal to absolute value of the component projection, u onto v, which is going to be u dotted with v over the length. The absolute value only has to be on the top, right? Because the length is always positive here. U dotted with v over the length of v. So these are what we have to compute. All right, u dotted with v. What's it going to be? Component by component. It's a times x1 plus b times all of this, right? So plus b times y1 plus c over b. And then that's got to distribute. And so this becomes ax1 plus by1 plus bc over b. That's just c, right? So plus c. So there's that. And then the length of v, well, that's just sum of the squares, right? Square root of the sum of the squares. Distance formula, two-dimensional, a squared plus b squared. And what we find then is that our distance is equal to absolute value of the dot product. So absolute value ax1 plus by1 plus c divided by the square root of the sum of the squares. All right, and that is exactly the formula. I'll scroll back up, but that's exactly the formula that we were told was the distance between the point and the line. Great, right? That's good. So back up here, Yeah, we got it. Now we want to plug in the point -2, 3, and then use this line right here. So now that we believe the formula, this is, by the way, in my opinion, the most important thing that we've done here, right? We've verified the formula. If we didn't know the formula to begin with, we would have derived the formula. Now we're just going to plug and chug, okay? So probably I can do this right over here. So the distance for this example right here is going to be, we've got all the pieces, right? This is our x1, y1, a, b, c. So our distance is going to be absolute value of 3 times -2 minus 4 times 3 plus 5 all over the sum of the squares, 3 squared plus -4 squared square rooted. And now we just have to simplify. So this is absolute value of -6 minus 12 plus 5 over square root 9 plus 16. Well, you might know that's a Pythagorean triple, right? But this then becomes what? 18 minus 5 is 13 fifths, right? And that's the distance between this point and this line, just like that.